Good morning, everyone. So last class we were discussing about um, binary weight network, and this class we are going to discuss about R2R ladder network. Already some part of introduction was already done in the previous class, and today we will go in detail explanation of R2R ladder network. So R2R ladder network looks like this as shown in the diagram. So wherein you will have n number of resistors which will be connected, R and 2R. These are the two resistors which we are going to consider in R2R ladder network. So that is the reason your name says R2R ladder network, wherein you consider resistor R and 2R. So these are the two resistors which you are going to consider in this ladder network, and the network is in the form of ladder. So that is the reason we say this network as your R2R ladder network. And your input, see, you have switches which are connected to your 2R, so it can operate as 0 or the high input, so 0 or 1, so it can be operated in that way. And so these are the inputs when we give, so whenever we give these inputs to your inputs of your R2R ladder network, or to R2R binary inputs, whenever we give, these are the output voltage you're going to obtain. We will see in some of the, at least one example, we are going to look into it, and we will understand in detail about your R2R ladder network. So suppose, let us say, we will consider for the input of B3 to be high and rest 3 B2, B1, B0 to be 0. So in that case, which is your B3? This is your most significant bit, and this is your least significant, LSB. Okay, so this is MSB and this is LSB. So this would be our B3. So B3 is higher in our case, and rest all would be 0. So here what happens is, this is your B0, B1, B2, B3 in binary input. So you can say B3, B2, B1, B0. Okay, so this would be arranged in such a way that B3, B2, B1, B0 would be your binary input, and this is your B3. So only this terminal is going to be high, means this is going to be connected to your voltage, and rest all is your 0. So what happens? How does your circuit looks when you connect B3 to be high? So this is your B3. So B3 is connected to your voltage reference, and this terminal would be grounded, and later these all are ground is going to 0. So that's where we have considered it to be ground. Okay, so this is very similar to the circuit. Okay, so initially you have 2R and 2R. So now we have to simplify these resistance and find out the equivalent resistance. How do you find that? When you simplify this, right? So 2R and 2R, first case, at this point, what is happening? These two are in parallel. So when 2R and 2R are in parallel, you will obtain the resistance to be R as R. Okay, so now R you have obtained, and this R would be in series to your this R. So R plus R is going to be your 2R. So now you have got 2R. So after simplifying these two, you obtain 2R. So now 2R is in, so these two already we have simplified, and for the answer for these two would be your 2R. So 2R and this 2R. So these two are in parallel. So now 2R and 2R are in parallel. So you obtain R. So again, this is in series with this. So again, this R you would have obtained from these two. This would be in series with this. So that is what is this. So R plus R is 2R again. So now these two are in parallel. So this 2R would be in parallel with this. So 2R would be in parallel with this, and when 2R is in parallel with this, you obtain R. So again, R plus R would be in series, so you obtain 2R. So you will obtain 2R, R plus R, again you will obtain 2R. So 2R again would be in parallel with this 2R resistor, and this resistor, which is your B3, which is going to your voltage reference VRF. We will consider it to be V reference, or voltage, anything you can consider, we will consider it to be V reference. So now these two, what you finally you've got these two, this in parallel with this, and you have resistor RF. Okay, so now to simplify this, you should go for using Thevenin network, Thevenin equation. You can obtain RTH and VTH. So RTH, what you will do, so both this will also be grounded and these two are in parallel, you would obtain R. This is RTH. Now VTH, how do you obtain? Apply voltage divider rule. V reference into 2R divided by sum of these two resistance. So when you simplify that, you would obtain R and R, 4R, no? 4R, R and R would be cancelled, 2 2s. So V reference by 2 would be your VTH. So, so after obtaining your RTH and VTH, how would your circuit looks like? It would look something like this. V reference, okay, which is in series with your input, which is RTH. This is VTH in series with their RTH. Then which is given to inverting terminal of your op amp, and here you have feedback. And yeah, so this op amp looks like your inverting amplifier. So inverting amplifier means, so what is the output you obtain? Minus RF by R1 or minus RF by R into V input. So here V input is your V reference by 2. So that's what we will substitute here. So voltage, since it is B3 binary, B3 is higher, so we will consider output to be V03. So for V03, your output is going to be, since it is an inverting amplifier, so minus RF by R into V reference, so or V input. So V input is V reference by 2. So since it is your by B3, so we will consider it to be V3. And B3 we will consider here. Okay, so this is for your output voltage of your, when your binary B3 is higher. Well, this case is when your binary B3 input is higher. Okay, so similarly, when you consider V2 to be higher and rest all binary input to be 0. Suppose B2 is higher and rest all input to be 0. In that case, so this would be high, right? And rest all input would be grounded. Means this would be given to your voltage reference and rest all would be given to ground. So in that case, what would happen? The output is going to be even this, like similarly you have to derive. When you derive it, you will obtain your output is going to be V reference by 4 into minus RF by R into B2 for binary 2 for B2. Binary input B2 to be high. Okay, in that case. Similarly, when your V0, your, let's say this input B1 to be higher and rest all to be ground, in that case the output is going to be your V reference by 8 into minus RF by R into B1. Okay, similarly when your B0, when this B0 is high, in that case you will obtain this output voltage, which is V reference by 16 into minus RF by R into B0. Okay, so now when you when you consider your all your inputs as your summing, when you convert your, if let's consider when you calculate all your inputs with the help of summing amplifier. Okay, so when you calculate with the help of summing amplifier, you know summing amplifier already. So output of summing amplifier is nothing but minus of all your inputs. Okay, so or minus of sum of all your so minus, so suppose if you consider all the resistors to be same, in that case minus V1 plus V2 plus V3 plus V4. Okay, otherwise you will have your resistors which are connected to it. So that is where we will consider here the RF feedback is same in all the case. So RF is same, so we will take it out as common. So minus RF into so one is V1 by R, V2 by R2, so V3 by R3 plus V4 by R4. So here V1 is nothing but your, okay, so V1 is nothing but your uh, V reference by 16. Okay, this is going to be your V1 LSB. So V reference by 16 R. So V reference B naught by 16 R. That's what. So in the place of V, we will substitute it to be B naught by resistor R. We will so here 16 R is there. So similarly, when you simplify here B1, okay, B1 by 8R, okay, so B1 by 8R, similarly B2 by 4R, B3 by 2R. So now all these we will divide it by the highest LSB value. We will divide it only these resistors. So when you divide it by 16, what you get? B naught by 16 would cancel out here. You would obtain only R. Similarly, here B1 by R by 2, here B2 by R by 4 plus B3 by R by 8. So this is what your output voltage you will obtain when you calculate by your summing amplifier.